Olá, pessoal. Boa tarde. Agora a gente vai dar continuidade ao nosso simpósio sobre Tisanoptera. E meu nome é Adriano Cavaleri. Eu vou estar mediando a próxima sessão, a próxima palestra, que tem como convidado o Dr. Manfred Ulitzka. O Dr. Manfred, ele é biólogo, ele é formado pela Universidade de Ulm, na Alemanha. E ele fez doutorado também pela mesma universidade, trabalhando com a comunidade de Thrips nas florestas da Alemanha. Né? Mas ele já fez projetos em vários países, inclusive aqui na América do Sul, trabalhando com os Thrips em copas de árvores na Amazônia, né? Na Amazônia das Guianas francesas. E, ultimamente, né, nos últimos anos, ele tem se dedicado com pesquisas incríveis envolvendo Thrips fósseis, especificamente Thrips que são depositados em âmbar. Né? Quem assistiu o Jurassic Park 1, lá o de 1993, vai lembrar o que é o âmbar, né? Mas é aquela resina que aprisiona organismos e que tem duração de milhões e milhões de anos. E essas descobertas que o Dr. Manfred fez nos últimos anos com os Thrips fósseis, eles trouxeram evidências muito importantes para a gente entender melhor a evolução desses insetos, né? E inclusive entender melhor como os insetos, os Thrips atuais, se relacionam. Então eu gostaria de chamar agora Dr. Manfred. Hello, Manfred.
Hello, Adriano.
How are you?
Fine, thank you. Thank
okay,
you for...
Can you hear me?
Yes, I hear you very well. You can hear also?
Yes, perfectly. So we are looking forward to see a bit more about these amazing studies about fossil Thrips, and I'm aware that you will show how you prepare them for study. That is also amazing. So I will let you now start your presentation if you want to share your slides right now. So you will have 25 minutes.
I also have some words for you, to the organizers. But good afternoon, ladies and gentlemen. Boa tarde. I'm very happy that this first Brazilian Phlaeothripidae Symposium has been organized as an online event. And I would like, first of all, to take the chance to thank all the organizers for this great opportunity to talk on this way to so many people, and of course for all the effort they have put in this. To introduce myself briefly, my name is, as Adriano told you already, Manfred Ulitzka, and I work on Thrips since many years as a private and freelance researcher, and most recently with a focus on taxonomy of fossil Thrips. The fossils I study are mostly amber inclusion, sometimes also copal. They come from different parts of the world, like the Baltic amber from Northern Europe, the Burmese amber from Myanmar, the Dominican or Chiapas amber, or also the Colombian copal, for sure, from Central America. My presentation today will also deal with this topic. By way of introduction, I would like to give you an impression of how to get from such a piece of amber. You can see two Thrips marked there, to the possibility of assessing all the necessary details and to study and to describe all these fossil inclusions. Then I will talk to you about Rohrthripidae, fossil Thrips from Cretaceous. Just tell me, can you see the first slide now, please, Adriano? Fossil Thrips are about 100 million years old. And I will talk about the hints they give us on the wing evolution within Tubulifera, one of the Thysanopteran suborders. But let me start by looking at this insect order a little bit more broadly. As you all may know, Thrips, the members of the order Thysanoptera, are small-sized, generally having a body length in between 2 to 3 millimeters only. Giant forms up to about 15 millimeters are known exclusively from the tropical extant or the subfossil fauna, like the one shown on the left. This is a subfossil inclusion of the species Anactinothrips gustaviae. It comes from Colombian copal and is accompanied by 4 phoretic or possibly also parasitic mites under its wings. What I would like to draw your attention to is the fact that the fossils I'm talking about are really tiny objects, as you can see in this comparison of a thrips with an aphid. Fossil thrips require special demands on preparation and also on the microscopic examination. Working on so tiny amber inclusions is quite a challenge, touching sometimes the limit of what we can do in paleontology. So let me first explain you how I do the preparing of the amber to create the necessary conditions to work on these tiny insect fossils. First of all, I prepare thin slices of the amber. These slices have a thickness of 1 millimeter only, sometimes even less, and they include the insect in the middle. Centering the thrips inclusion midway with its head downwards, these slices are embedded in a polystyrene resin. After the synthetic resin has hardened, the blanks are removed from their molds and are ground again. These works usually are done using a water-fed flat lap made from a modified pottery disc with diamond grinding wheels. And very fine works I even do with Japanese wet grinding stones for knives. On the left, you can see such a thin amber slice, and on the right, the almost ready slide. That is finally ground and polished again to the size of a standard microscope slide and a thickness of about 2 millimeters only. These resin slides are clear like glass. The synthetic resin stabilizes the amber and prevents its oxidation. Furthermore, centering the tiny inclusion with the head downwards, as also done with extant thrips mounted on slides, makes the handling and comparing with other specimens much more suitable, without always searching the object under the microscope. Over and above the size of the microscope slides, simplifies storing these samples in normal, standard slide boxes. This method can also be used with copal, as you can see here with the Streptothrips from Madagascar copal. Polystyrene resin preserves copal excellently, without any risk of dissolving the surface and thus destroying the fossil. Let me give you some impressions what is possible with that method. This first sample shows specimens of Archancothrips from Baltic amber. Even after 40 millions of years, details like the presence of a thoracic spinula or the palps at the mouth cone are clearly visible. And what is more, you even can assess character states of the antenna, like the typical thorn distally on segment 2 or the sensoria on segments 3 and 4. The next slide shows an interesting species from Dominican amber. It has a quite strange shaped second antennal segment and conspicuous 4 tarsal structures with a large tooth and a hamus consisting of 3 discrete finger-like spines. It is associated with Phlaeothripidae. But we can see more. Fungal spores, indicated now on the left, are attached to the body, and they allow to draw conclusions that this species was a fungus feeder, similar to extant members of Phlaeothripidae, and thus it probably also had lived in similar habitats. But let me now come to thrips from burmese amber. Burmite is known to preserve a great diversity of fossil arthropods, particularly insects. Nothing, however, had been published on thrips from Burmite until 2018, until my paper describing Rohrthrips pankovskiorum and the tubuliferan family Rohrthripidae. Rohrthrips, the first one mentioned, is a very common fossil in Burmite. Some pieces of amber are known, including more than 150 specimens. Possibly, these thrips had a similar swarming behavior as today's thunderflies, and possibly they once were just as annoying for the dinosaurs as some extant species are today for us when they do their mass flights. But I don't want to go into detail on this species. I'd like to come straight to Rohrthripidae. This picture shows Rohrthrips burmiticus, which was described in a new family, the Rohrthripidae. You will have seen immediately the differences between this specimen and the Rohrthrips shown before. The order Thysanoptera in general is classified into two suborders, Terebrantia and Tubulifera. Terebrantia is mainly characterized by the presence of a distinct ovipositor. Tubulifera by a tubular-formed 10th abdominal segment. Tubulifera is the largest suborder, including over 3,500 species. Recognizing subgroups within Tubulifera, however, is exceptionally difficult because much of their diversification has involved the reduction or loss of characters, and homoplasy is evident. In the extant fauna and from younger fossils, the family Phlaeothripidae generally is regarded as the sole member of the suborder Tubulifera, whereas Terebrantia comprises all other families. But now, what makes Rohrthripidae so special, having required the establishment of a new family within Tubulifera? The genus Rohrthrips dates back a bit longer to the oldest known specimen of Tubulifera, Rohrthrips libanicus, coming from Lebanese early Cretaceous amber. The authors had chosen the name according to the German word for tube, Rohr. Unfortunately, its head is missing, but otherwise it is a quite well-preserved fossil. The first thing catching the eyes are two longitudinal veins, the first one furnished with several setae on the forewings. This feature is interpreted plesiomorphic. In modern Tubulifera, the Phlaeothripidae, the wing veins are completely reduced, what you can see in the picture on the top left. And there is only the indicated short subvessel remnant with 3 setae present at the extreme base of the wings. In contrast, in all members of Terebrantia, wing veins are present. But this is not all. Having a typical tubuliferan body, this first species of Rohrthrips, Libanicus and Burmiticus, show further terebrantian plesiomorphic feature, first of all on their wings. The wing coupling mechanism, for example, is identical to the one found in Terebrantia. I will come back to that later. The wing fringes are placed on sockets, quite similar to those in Terebrantia. Normally, in Tubulifera, the fringes are deeply embedded in the wing membrane, but never their own sockets. However, although tubuliferan features can be found on the wings, like the smooth wing membrane without any microtrichia, and the equal length of the fringe hairs on the anterior and posterior margin on the forewing, that you can see in the picture in the middle. The maxillary stylots are also similar to those of modern Phlaeothripids, deeply retracted into the head, quite similar to those of extant species of Rohrthrips. A further plesiomorphic feature, however, concerns the antennae. In Rohrthripidae, they are 9-segmented, whereas the antennae in Phlaeothripidae are never more than 8-segmented. The establishment of Rohrthripidae was based on the above-mentioned plesiomorphic features with respect to extant Tubulifera. It is certainly a compromise between respecting strict phylogenetic principles and the practical manageability of classification. Therefore, Rohrthripidae was defined neither as a stem group nor as an obligatory sister group of Phlaeothripidae, but rather as one of many presumed branches of an early diversification. Rohrthripidae potentially is paraphyletic. However, the establishment of this family provides an elegant solution of differentiating these early ancestral Tubulifera without redefining Phlaeothripidae. Later studies on burmese amber revealed 5 new species of Rohrthrips, males and females. Concerning shape and length-width ratio of their tube, these species can be classified into 2 subgroups. The first one with a rather short and bulky tube, and the second group with a long and slender tube. This species, seen on the right, has an interesting wing vein. It is short, possibly reduced, and it is distally split, ending with 2 terminal setae. Therefore, it was named Schizovenatus. New finds are allocatable to the described species. Recently, I could identify a second female of Rohrthrips patrickmilleri, a first male of Giavene, and a first female of Rohrthrips mariae. However, there is more amber, not yet prepared and polished, and I'm very curious to see what the new findings will show. The one on the top might be a second find of Schizovenatus. And now the sad part of my talk. A new further species was already known. It was a donation from Mary Pankowski. She bought it from a Chinese seller. It was rejected by the German customs and sent back to China. Unfortunately, on its way back, it got lost. The missing species is a rather large one, with long antennae and a long and slanted tube. It has a pale, possibly translucent wing vein, meeting the costa near the wing apex in 2 conspicuously longitudinal brown spots. There are many characteristics found in these specimens supporting the association of Rohrthripidae with Tubulifera, like thoracic structures or the position of the abdominal spiracles. One thing I want to show you today more in detail is a tubuliferan feature rarely studied, the surface of the wing patterns. Usually, these patterns remain hidden in slide-mounted samples due to the refractive index of the mounting media being nearly equal to that of the wing membrane. In the 1990s, Batty proposed a special preparation technique to make these delicate sculptures visible. It reveals primary surface patterns showing tiny lines, wrinkles, and secondary surface pattern like humps or elongated ridges. These patterns even have been discussed as tubuliferan wing veins, but they rather are structures giving the wings rigidity. In terebrantia, these patterns are not developed because their wing membrane is stretched between the veins, and possibly it obtains additional strengthening by its pubescence with microtrichia. In amber inclusions of Tubulifera, as seen here in polygonal thrips from Baltic Eocene amber, the surface patterns sometimes are visible, possibly due to a thin embedded layer of air around the wing surface. But in fact, making the surface pattern visible does not require any preparation technique at all. It just requires higher magnification, and then it is simply recognizable even in specimens still alive, like here in Thrips huitzili. In Rohrthripidae, the pattern is particularly visible where the wings overlap. It forms a wrinkled structure, and towards the wing base, longitudinally striations. Secondary surface patterns, however, are not really accessible. They may be redundant due to the rigidity provided by the wing veins. The wings of Tubulifera and terebrantia are essentially different. Therefore, the development of the tubuliferan wings had been subject of debate for a long time. The distal 3/4 of the wings had been even discussed as a secondary neogenic development from a former micropterous condition. The wing structures found in Rohrthripidae, however, contradict this suggestion of the tubuliferan wings being not directly homologous with the wings found in the rest of the Thysanoptera. You already may have realized some of the interesting features in these pictures. In terebrantia, the wing fringes arise from sockets, and this provides a collapsible system for the fringes to be locked in two positions, one for flying and one for parking the wings. This has been interpreted as preventing the fringes from tangling when the wings lie parallel at rest over the abdomen. In Phlaeothripidae, the wings overlap when not in use. Thus, a similar parking problem does not arise. Their fringes are embedded immovably between the cuticular layers of the wings. In Rohrthripidae, the fringes clearly arise from sockets. However, there is reason to doubt their function as part of a collapsible system. None of the fringes of any Rohrthrips fossil is snapped into a resting position, or at least it is kinked at its socket. Furthermore, not all the sockets are placed at the extreme edge of the wing. Some clearly are recessed into the wing membrane, and therefore the relevant fringes definitely remain immovable. These findings may indicate that the sockets have been modified, recessed, and reduced from an ancestral form, and that the collapsible fringe system was given up in Rohrthripidae. Concerning the wing veins, the findings lead to the conclusion that the short basal wing vein present in Phlaeothripidae also is a plesiomorphic feature that resulted from the reduction of a former well-developed longitudinal first vein in ancestral Tubulifera. Thus, the subbasal setae may be interpreted as wing setae that simply were moved towards the base within this process. The similar microscopic sculpture of the first vein in Rohrthripidae and of the basal vein in Phlaeothripidae may substantiate this hypothesis. In fact, various features of the modern tubuliferan wing seem to have developed similarly. That means plesiotypically and by reduction of ancestral character states, becoming visible in Rohrthripidae as kind of evolutionary intermediate stages. The forewing clavus of Rohrthrips, for example, steer where setiform processes at its tip, and the hindwing a basal recurved seta representing a functional coupling mechanism similar to that of terebrantia. In contrast, wing coupling in Phlaeothripidae consists of small hooks at the hindwing catching a ventral ridge on the clavus of the forewing. The former paired setiform process, however, is still present in Phlaeothripidae as a small, most likely functionless rudiment apically on the forewing clavus. Another feature to be considered in the context of reduction is the structure of the wing membrane. In Tubulifera, it differs conspicuously from that of other Thysanoptera in lacking surface microtrichia. In the main, this applies to both to Phlaeothripidae and to Rohrthripidae, with one exception. Rohrthrips patrick-mülleri shows some sparse microtrichia at the extreme base of its hindwings. This rudiment, or possibly an atavism, is an important finding which indicates that the membranous tubuliferan wings derive from a pubescent ancestral form. All things considered, the present results refute the belief that the tubuliferan wings are even part of them are neogenic. Definitely, these organs are homologous to those of other Thysanoptera. However, the wings are characterized by plesiotypic ancestral character states, which have been reduced or even completely resetted. Each fossil reveals secrets, and as mentioned before, sometimes we are lucky enough to get information, even on the diet or hints on the habits where the ancestral thrips lived. In some amber, fungal spores were present close to the Rohrthrips inclusions. However, in Schizovenatus, it became even more evident that these thrips were closely associated with fungi. Examinations using transmission light revealed that its inside of the body is covered with fungal spores, which only could have been ingested as food. This suggests a feeding habit similar to extant Idolothripines. As a consequence, these thrips must have lived in habitats providing suitable fungal spores with dead branches or leaf litter. This conclusion corresponds with a concept suggested by Batty for ancestral Tubulifera, as insects having cryptozoan habits and seeking fungal hyphae and spores, the proto-Tubulifera. Let me finish this presentation with an outlook into the future. Regarding extant Tubulifera, we see a great diversity of species mainly associated with dead plant tissue, feeding on fungi or on products of fungal decay. Others are leaf feeding, breed in flowers, and a few are even predatory. But where this diversity once derived from remains an open question. Rohrthripidae is certainly just one result of many attempts evolution has gone on the way to modern Tubulifera. And there are still many puzzles to solve. But never forget, each fossil reveals secrets. Have a look at this astonishing tiny specimen. It is only 0.7 millimeters long. It comes also from Burmese. It has 8 segmentic antennae and narrow wings, like the members of Phlaeothripidae. However, there are 2 wings veins clearly visible in the forewings. 2 specimens of this strange thrips are waiting to be examined. One is already at DESI in Hamburg to get a synchrotron microtomograph. And I'm very curious what they will tell us about the evolution of Tubulifera. Will they reveal the origin of Phlaeothripidae, or are they just another dead end of evolution? With this question, I have come to the end of my presentation. On my website, you can get more information about my research on thrips. And to keep up with current projects, don't forget to follow me on Twitter and Instagram. Many thanks for your interest. And now I'm ready for your question and looking forward to them. Thank you very much.
Okay. Claps for you, Manfred.
Thank you.
Thank you for this amazing presentation. It was very, very, very nice. I will speak a little bit in Portuguese right now.
Yes.
Pessoal, deixem suas perguntas aqui no chat. Perguntas sobre a apresentação do Dr. Manfred, sobre os Thrips fósseis e uma descrição recente de uma nova família de Thrips, que é um fato realmente uma das mudanças, uma das novidades taxonômicas mais, enfim, impressionantes nos últimos anos dentro da ordem Tisanoptera. Não só pela descoberta desse novo grupo, mas pelas características que esses fósseis apresentam e que são características de estados intermediários entre as formas que a gente conhece atualmente. E por isso trouxe uma visão mais refrescante, nova, do que a gente conhecia sobre os Thrips. I will ask you some questions from the audience.
Yes.
Let me see what we got. We have one from Ellison. How difficult is the process of finding such minute insects in amber inclusions among so many other things inside? And I would add a part on it. How many hours do you spend to get these polished amber inclusion for taxonomic study? Because I'm aware that it's a block of amber, and you have to work on it.
Okay, so I have some amber collectors and amber sellers, and they are already seeking the Thrips. And if they have a Thrips fossil, they send some pictures, yes, what you can see on a picture made in a complete amber piece. And then if I have bought the amber, this is a process of many hours, because I have to cut the amber, and then I have to grind the amber to get the Thrips in a position that I have to see it, that I can see it mostly dorsoventrally. This is very important for Thysanoptera, because all the features are described dorsoventrally, so you cannot work on lateral Thrips. And then I grind the amber and I polish it, and this sometimes takes many hours. Yes, this is really hours of work. And to preserve the amber, it is embedded, as I have told you in my presentation, in this polystyrene resin, in a synthetic resin. And then it really begins, because the resin has again to be polished, to be ground to the microscope slide. And this is also about 2 hours of work to finish it. So in each of the microscope slides of a fossil Thrips, there are 4 to 5 hours just work without any descriptions.
Yeah. Good. I imagine that how hard is it? Edison is telling mounting Thrips is hard, but mounting fossil Thrips is even harder. Congratulations on your work. Actually, I have
to break the wings and the antennae.
Yeah,
in the racing.
I have you have better slides of Thrips in amber than many of my slides mounted in balsam. So let me show you another question from Guilherme. On your opinion, which country have the best quality amber to study? And I will add a part of it. If we are interested in studying Thrips in amber from South America, where can we find good material on it?
Okay, I begin with the first question. You have good quality amber in any sites of the world. There is burmese amber, which is very clear, but there is also burmese amber with many sub-inclusions that hide the fossils. The same is with Baltic amber, which is about 40 million years old. There are big pieces, completely clear, and sometimes there is humidity in the fossil resin, and then you can't see the specimens, and you can't describe them. So this is not an answer to give where the amber comes from, because you just have to check the quality before you work on it. You can find it everywhere. This year I have published a small piece of Ethiopian amber, a very, very clear piece of amber, and the African amber is very, very rare. So this was also like to get this piece.
Yep.
Yeah.
Where you describe Rohrthrips, isn't it?
Yes, the Rohrthrips, yes.
Yep.
And from South America, there is not really amber in South America. It's in Central America. There's the Mexican Chiapas amber, and some fossils are known. I have an Eneothrips, which is waiting to be described. And I know there are some Tubulifera also in different museums, but not a lot. And then you have the Dominican amber, and there are some interesting thrips. Not described yet. The first one was the Chiriduro thrips I've showed you with the asymmetric antennal segment 2 and the strange-shaped tarsi.
Good. There's another question asking, let me share here. And it's in Portuguese.
So you have to try.
Yeah. Elisa, one of our colleagues, in the amber, when you, in which you find thrips, do you usually find another groups of insects as well?
Oh yes, of course. Most insects in amber are Diptera, and thrips are only 1% of all the inclusions. It's not a lot. Thrips are not.
It's tough to search in so many amber inclusions to find a thrips.
Yes, but with fleas it's even worse. Fleas are very rare, and from Baltic, I think only 2 or 3 are known.
I can imagine. I have a few questions on my own. You told that the Rohrthripidae family is potentially paraphyletic. What's the evidence of it? And do you think that some of the forms that we observe today of Tubulifera might be maybe relatives of these or derived from these fossils that you find it?
I don't think so. I didn't describe this family as a sister group of the Phlaeothripidae. I think there must have been something else, and I think diversity is not just 2 branches. There is, it's like a tree. There are many branches, and evolution tried many possibilities. And I think Rohrthripidae is not directly in front of the Phlaeothripidae. I don't think so. But possibly the one I showed on the last slide, I don't know. It's really very similar to the Phlaeothripidae, but it is so small, I cannot see it with the light microscope. And I hope to get a solution with microtomograph.
Yeah, we hope to. We are very anxious to these new findings. And you showed us some beautiful images of the spores, fungal spores inside the fossils, which it's very. We believe that they are feeding on it, just like some of the extant taxa on idolatrip pines. Do you think that they could live in rather than the leaf litter in the crevice on the trunks of the trees, where it's easily to be covered with the amber from trees? Because I'm just thinking how insects on the leaf litter can be involved with these amber inclusions.
This is possible because the resin has also dropped from the trees. So
oh, I see.
This possibility exists, but we cannot say if they have lived on bark or on dead wood or in the leaf litter. We just know they certainly have lived on fungal spores because they're inside the body, and the way to get there is by food.
That's true. And I will ask one question from Carlos de Bourbon. That is a question that is, I think it's worth to know, is how old is this fossil family, and how old is what is the oldest amber inclusion for Titanophora?
Well, this family from burmese amber, the Rohrthrips from burmese amber, they're about 100 millions of years old. They come from late Cretaceous. And the first Rohrthrips described as Libanicus from Lebanese amber, it comes from early Cretaceous amber. So this is a bit older, 120 millions of years. And these are also about the oldest amber fossils. I have heard that there is Jurassic amber in China, but I don't know if the story is true or not. It would be great.
Okay. Let's see and wait for it. Yeah, it's impressive. Observing something in an inclusion of more than 100 million years ago. It's like a photograph of the past. So yes, the insects are all there like they were millions and millions of years ago. How is this the feeling of receiving a sample that you get and looking in the past of these insects?
It's always like a present. And it is even more if you find some sub-inclusions, for example, like the mites under the leaf, under the wing, excuse me, or if you find sub-inclusions like a fungal hyphae, fungal spores, or something like that, because then you can really talk about ecology. You can talk about the ecosystem, about the conditions in this thrips lived.
I truly agree with you. So it's not the individual, the specimen, but there's a clues of something on their lives, where they live, which organisms, with which other organisms they interact. So it's amazing, simply amazing.
And sometimes you even have bacteria in the amber. And Ethiopian amber, there were bacteria and also fungal spores. So we could say this species is also living in decaying plant material.
Perfect. Well, we are in time, but I would like you to thank you very, very much, because it was a pleasure to see your work.
Thank you for the opportunity.
Yeah. And I will recommend visiting Manfred's website if you like Thrips photographs, if you like Thrips information. So go to his website, follow him in the Instagram and on the Twitter. Then you find beautiful pictures of Thrips, the best one I ever seen. So
Thank you so much, Adriano. And I wish you a further good presentations, interesting presentations, and a good meeting. And thank you that I could participate.
It was a pleasure. So you are invited to stay watching the next presentation. So,
yes, for sure.
Thank you.
Yeah.
Bye.
Goodbye, Adriano.
Pessoal, a gente vai fazer uma breve pausa agora, depois dessa apresentação do Dr. Manfred. E a próxima palestra vai começar em instantes, daqui a 15 minutos, vai ser com a Mariana Lindner, que vai falar sobre um grupo muito interessante de Thrips que induz alterações nas plantas, que é o gênero Holopothrips. Então, daqui a instantes a gente volta no canal e dúvidas, né, sobre os certificados vão ficar passando ao longo das apresentações, mas não há controle de presença e não há também nenhum tipo de cadastro que vocês têm necessidade de fazer, tá ok? Até daqui a pouco.